Hey, welcome back, everyone. I am going to continue reviewing, like previewing, I would rather say, the content here that I was reviewing from yesterday. So, I'm, we were here, so we were on the hemoglobin oxygen dissociation curve. And this CADD thing, I have no clue what it is. I'll definitely search more about it. I'm starting to remember that this dissociation curve shifts to the right or shifts to the left with these five factors, which is CADDs. So it describes the factors that if you increase them, you get a right shift, which is the Bohr effect. So we can always ask our questions. So this is all in the same topic, which is oxygen, hemoglobin, dissociation curve, and what is Bohr effect. And this might be related to related to chemistry and perhaps organic chemistry. We'll see. So if you increase CO2, your dissociation curve shifts to the right. If you increase your acids, you go to the right. If you increase your 2,3-DPG or BPG, what is 2,3-DPG? And if you increase exercise, which is basically the same as increasing acid coming from lactic acid and the CO2 in your blood, and also increases the temperature of your body. So mainly I need to dig deeper into knowing what is 2,3-DPG. Now here we have that a right shift decreases the hemoglobin's affinity for oxygen. I like to think of this as the hemoglobin HB dumping oxygen off or delivering it to tissues. Okay. A left shift increases the HB's affinity for oxygen. Oh, okay. So the more you go to the left, it increases the HB's affinity for oxygen. A right shift decreases the affinity for oxygen. HB's affinity, to be more specific. I like to think of this as the HB dumping oxygen off or delivering it to tissues. Makes sense, right? So the HB dumps oxygen off or delivers it to the cells, tissues, and it's more when you're rested, right? When you're exercising, when you're increasing your temperature, your the cells give more oxygen to the blood to be circulated, right? But when you're rested, your cells are getting that oxygen, which is like a fuel for them. And we also know from the ETC that oxygen is basically the main contributor for generating ATP. We'll definitely dig into that when we go over carbohydrate metabolism, glycolysis, and ATC, and all that. A cofactor is a non-protein molecule that binds to a protein and is needed to help that protein carry out its function. There is a subtle difference between cofactors and what was it? We'll come to it. So HB's main cofactor is called heme, and it's this cofactor that contains the iron characteristically associated with blood. So we know that blood is characterized with having iron, and this iron, the ferritin, is attached to this cofactor, which is the heme part of hemoglobin, HB. And we know that HB is a subunit, one of the 4 subunits of hemoglobin. Now we go to the immune system. T helper cells marked by CD4 on their surface. Their goal is to support and help activate cytotoxic macrophages and B cells. They can only see an antigen on MHC2. Remember the rule of 8s. MHC1 goes with CD8. 8 times 1, 8. MHC2 goes with CD4. 2 times 4 equals 8. Nice. We have a YouTube link too. We'll come back to this. This is all the same concept. Humoral immunity. B cells ingest a pathogen and present an antigen to a helper T cell, which activates the B cell to crank out a ton of antibodies. This differentiated B cell, which is now functioning as an antibody factor, is called a plasma cell. So, first thing mentioned here is humoral immunity, and then we know that in humoral immunity there are B cells that ingest a pathogen and present an antigen to a helper T cell. So when these B cells ingest the pathogen, they can present an antigen to a helper T cell, which activates the B cell to crank out a ton of antibodies. Okay, so like the cycle is like the B cell ingesting the pathogen, and then this the helper T cell, they can present it to a helper T cell, and with the help of the helper T cell, the B cell that had ingested the pathogen is able to produce antibodies. And this differentiated B cell, which is now functioning as an antibody factor, is called a plasma cell. Nice. So if they ask you what is a plasma cell, you know that it's a B cell that has changed its function and is now an antibody factory. Cool. Easy peasy. You have 4 different clauses for this one. So next concept is that cytotoxic T cells marked by CD8 on their surface, they kill cancerous and infected cells by recognizing an antigen on MHC1 cells. So rule of 8s. MHC1 goes with CD8. 8 times 1 equals 8. MHC2 goes with CD4. 2 times 4 equals 8. Cool. So we have cytotoxic T cells as well. So we know that the B cells were collaborating with the helper T cells. Now there's another type of T cell, which is the cytotoxic T cell, and it is marked by CD8 on the surface, and they kill cancerous and infected cells by recognizing an antigen on MHC1 cells. So they recognize MHC1 because there's CD8, 8 times 1 equals 8. You want the total score to be 8, right? And if it's a CD4, if there is a MHC2, sorry, we need to know definitely what is CD8. So CD8 is like a receptor or like a cell marker. It's like marked by these CDs that are on the surface, right? So you can imagine the old computer CDs to be on the surface of the T cells, right? Cytotoxic T cells. So they have so we can ask this from ChatGPT, right? Are the CD8 or CD4 first we can ask what are the CD8 CD4 markers, and are they on the surface of the virus or the cytotoxic T cells. And now we're in immune system. We're going to organize all of these later, okay? No worries. We have all the time in the world. And it's December 20th, so we're gonna be together for a long time. Now, as far as I'm concerned, is to know that MHC1, the MHCs, are antigens. So they are by recognizing an antigen on MHC1 cells. So we have MHC1 cells and MHC2 cells, right? Do we have 3? We'll figure out what are MHC1 and 2 cells. The cytotoxic T cells, again marked by CD8 on their surface, they kill cancers and infected cells by recognizing an antigen on MHC1 cells. The cell-mediated immunity uses T cells to kill affected cells. So we have another immunity. We had the humoral, which was the B cells, right? Getting help from helper T cells. And we have here cell-mediated immunity, which is literally the T cells killing affected cells. We'll figure that out in the YouTube video. We have the adaptive immune system, which has the ability to differentiate pathogen versus host cells. It's cool. So if it's adaptive, it can differentiate between the pathogen and the host cell. And then we have the key characteristics of the innate immune system, we have non-specific versus specificity. We have fast response, minutes to hours, with regards to speed. No memory associated with the response memory. When you're thinking of innate immunity, think of things like skin, stomach acid, etc. These are barriers that protect our body from organisms, but that protection is not an aimed process. I'm trying to figure out what I just read. The key characteristics of the innate immune system. So we have adaptive and innate. It's fast response, non-specific, no memory. When you're thinking of innate, think of things like skin, stomach acid, etc. So it's pretty much like passive, and it's first barrier, right? These are barriers that protect our body from organisms, but that protection is not an aimed process. Cool. It's not aimed, okay, right? Adaptive is it can differentiate between host cells and the pathogens. And then we also have okay, cool. So we know that the innate is non-specific, whereas the adaptive immune system is specific. We know that the innate immune system is fast, but the adaptive immune system is slower because obviously it takes some time to differentiate between the host cells and the pathogens. Also, there's no memory associated with the response for the innate immune system, but for adaptive immune system there is a strong memory associated with the response, like you can think of antibodies. This is the immune system responsible for vaccine conferred immunity, exactly, so it can be safe for months, and we all experienced that with the COVID. Now we have the sorry, we have the humoral immunity, which kills extracellular pathogens. Okay, think about things like bacteria that are just chilling in your interstitial space, secreting toxins and whatnot. So again, humoral immunity kills extracellular pathogens. Think about things like bacteria that are just chilling in your interstitial space, secreting toxins and whatnot. Cell-mediated immunity is used to kill intracellular pathogens. So the humoral immunity killed the extracellular pathogens. The cell-mediated immunity, cell-mediated intracellular. So if it's a cell-mediated, it's inside the cell. Pathogens, right? If it's a humoral immunity, it kills the extracellular pathogens. So humor comes from the liquids, I believe, that we have in our body. It comes from ancient Greece. So if it's about the humor, it's about the outside of the cell, like whatever liquid, which is mainly blood, plasma. In the lymph nodes, we have whatever it is in the lymph. We'll also learn more about that. And yeah, so that humor, if it's humoral immunity, it's basically inferring that it happens outside of the cell. And bacteria are just chilling in your interstitial space. Where is the interstitial space? And we need some pictures. Oh, it would be cool if I'll figure that out. Like if I could make 3D branches, and that would help to understand all these, like connect all these concepts. Um, that's for later. We have cell. Yeah, so we read that. So again, humoral immunity is like bacteria chilling in the interstitial space, and viruses and cancers, or like cell mediated immunity, because you use that to kill intracellular pathogens. So yeah, viruses go into our cells, or cancers that are inside the cell. They're an inside cell pathogen. So yeah, that's when you use cell mediated immunity. We have a B cell, which has been activated to create antibodies. It's called a plasma cell. We read that. We understood that. Cool. The B cells that do not get activated into plasma cells can get activated into memory B cells. So the next time you encounter that specific organism, you already have a blueprint for the antibodies that will kill it. Cool. So if these B cells don't turn into plasma cells, they they turn to they turn into memory B cells, where it's like literally a memory thing, where they keep it in their head. They remember that this pathogen came a long time ago, and now I need to kill it. So you already have a blueprint for the antibodies that will kill it. This is mainly how vaccines work. 3 antigen presenting cells are B cells, macrophages, and dendritic cells. Big Mac Daddy. So, whatever that is, Big Mac Daddy. Big Mac Daddy makes sense. 3 antigen presenting cells. So these cells, these Big Mac Daddy cells, present antigens. It's B cells, macrophages, and dendritic cells. There's a YouTube video on that. We'll definitely study that. Now we go to the insulin glucagon. We know that insulin reduces, like, helps the cells to absorb glucose, and so it takes glucose from blood, and glucagon is the reverse. So it releases glucose into the blood. So insulin increases glycogenesis. We know glycogenesis is making glucose from glycogen, right? And glycolysis, so glucose metabolism. It increases glucose metabolism, right? So it helps to uptake glucose, to bring it into the cells from the blood. And it increases lipogenesis. And we know that lipogenesis is creating fat, right? Generating fat. We'll make sure that we get that correctly. So then we have insulin glucagon. What is lipogenesis? Insulin helps blood sugar, glucose, enter the cell to be used or to be stored. as glycogen in the liver or through the conversion of glucose to fatty acids. So insulin helps blood sugar, glucose, enter the cell to be used or to be stored as glycogen in the liver. Cool, yeah. So when the cells uptake the glucose, they can either use it, this glucose, this blood sugar, blood sugar glucose, either enters the cell to be used or to be stored as glycogen in the liver, or through the conversion of glucose to fatty acids. Oh, we can also, the third option is to convert it into fatty acids. Think of insulin as the fed state hormone. So when you're fed, when you're not hungry, when you're satiated, insulin is the hormone for that. It causes you to be in that state, to be fed, right? Or is it that okay, let's not get confused. Does insulin cause a fed state, or is the fed state causing insulin to be secreted from the pancreas B cells, right? We'll study more about that. And then we have glucagon. It should be the reverse role for glucagon, right? So glucagon increases glycogenolysis, glycogen olysis. So lysis is breaking down. So it should help with breaking down glycogen. We know that insulin was not breaking down glycogen, it was making glycogen because it absorbed glucose to be stored in the liver to make glycogen. So it helped with glycogenesis. So you have glycogen, and when it's SS at the end, it means that you are generating glycogen. And yeah, so when you're glucagon is has the reverse function, and it increases glycogenolysis, so breaking down glycogen. And it increases gluconeogenesis. So gluco comes from glucose, right? Neogenesis. So we know that you can also make glucose from let's bring it here. We had it here, right? Yeah, we had it here. Okay, can we search in this? Gluconeogenesis, perfect. So this is the chain for gluconeogenesis. And we need to know all these things, but we'll have it. Cool. So you can see that you're making glucose. Like your end goal is to make a glucose. It takes place mainly in the liver and to a lesser extent in the kidneys. So making glucose happens in the liver. Exciting. We know that in the liver you also store glycogen, right? And the first step of this chain is the pyruvate that turns back into glucose. for glycolysis, we had that the from glucose you were making pyruvate, right? And most likely these molecules, sugars in the middle, should be the same between gluconeogenesis and glycolysis, but we'll go over that later. Glucose metabolism increases. So glucagon increases gluconeogenesis, right? And glucose metabolism. Sure. It metabolizes glucose. Wait. Kind of doesn't make sense. Because if you're metabolizing glucose, then it is the effect of insulin, not glucagon. So we need to make sure that we know what is glucose metabolism and does glucagon increases that. And it also increases lipolysis, so fat metabolism. If insulin, like we need to, how can I understand this relationship better? Glucagon increasing, is it breaking down fat or making fat? It is breaking down fat. So is it also breaking down glycogen, right? Increasing glucagon, increasing lipolysis and glycogenolysis. Activates hormone-sensitive lipase and decreases acetyl-CoA carboxylase activity. Hormone-sensitive lipase. It breaks down fat, right? Lipase, it means that it cuts down fat. It activates it. And acetyl-CoA carboxylase. So acetyl-CoA is in the Krebs cycle mainly, right? And glucagon decreases the acetyl-CoA carboxylase activity. We need to know where does acetyl-CoA function? What does it play a role in? We have glucagon, which helps mobilizing stored energy for the body to use. So glucagon helps mobilizing stored energy for the body to use. We have the stored energy in our livers, and glucagon helps it to get mobilized. Makes sense, totally. This means breaking down stored sugars like glycogen from glycogen and mobilizing stored fatty acids from triglycerides as well. Okay, now it all makes sense, right? So we have our question kind of answered, as we know, but we need to definitely know it more in detail on how glucagon increases lipolysis and glycogenolysis, right? Like, what is the chain of reactions that take place? And think of glucagon as the fasting state hormone. Again, the same question. Does glucagon cause the fasting state, or is it the fasting state that causes glucagon to get secreted? I suddenly know that the answer is the latter. So the fasting state causes the secretion of glucagon, right? You're fasted, you get hungry, you need some energy, so glucagon is secreted to uh, to release these sugars. I know a cool fact. I know that all these drugs, like insulin drugs, they kind of work by mimicking glucagon. So, for example, you see these famous drugs, Ozempic or Mounjaro right now. These are GLP-1 and GIP-1, and GLP stands for glucagon-like peptides. So they mimic glucagon by breaking down the glycogen and source of carbs in our liver, so you're not hungry anymore, right? So it is the fat state here that also causes insulin to be secreted. We can cross it off, right? The ones that we answer. Okay, next thing is that we have the Krebs cycle. This is the picture. We'll definitely can expand it here, right? NADH is created in the conversion from malate to oxaloacetate. Oh, so for Krebs cycle, we just need to know every single step in detail of these cycles, right? Malate, like NADH, is created in the conversion from malate to oxaloacetate. Where is that? Do you see malate? Oxaloacetate, oxaloacetic acid should be that. Malate, same shit, same thing. Excuse my language. So NADH is created. I also need to know like what is specifically NADH and what is different between NADH and NADPH. Same for FADH and FADH2, like NADH2, whatever those are. I know it's like about the concepts of electron transportation, right? Electron acceptance, getting oxidized, getting reduced, or electron donation, getting oxidized. We will figure that out. NADH is created in the conversion from malate to oxaloacetates. Okay, yeah, same thing. NADH and CO2 are created in the conversion from alpha ketoglutarate to succinyl CoA. Succinyl CoA, where is that? Okay, here. So NADH and CO2 are created here. Man, there should be some way to memorize these. Like, imagine you're stressed out in the exam. That's literally how I was. And you don't know, like, how to bring these up in your memory. It's all gone. Again, NADH and CO2 are created in the conversion from isocitrate to alpha ketoglutarate. It's one step before that, step 4. GTP is created in the conversion from succinyl CoA to succinate. We have something here. Succinate goes late Succinate is after succinyl-CoA, and the conversion makes GTP. That's a cool mnemonic to remember. Succinate is late. It goes after succinyl-CoA. We can also see it here, the succinic acid, succinate, is after succinyl-CoA. And GTP is, where is that? Where is GTP? Succinyl-CoA, ATP, CoA, succinate. I don't see any GTP here. I think it's not written in this thing. Let's see if where is the Krebs cycle? So we have succinyl-CoA, getting out ATP, and I don't see even any GTP here. It's either mistake in the flashcard, so we can ask here. These are questions that we are going to ask from ChatGPT and other, and find the information from other resources. Is it GTP or ATP that is, or both, that is produced from the conversion of succinyl-CoA to succinate, succinyl-CoA to succinate. Sometimes you ask yourself, why am I doing this, right? Why is this even important? This is important because you want to be a practicing physician, and that is why this is important. So your professional life depends on this. Your patient's life depends on this. Haha, gotcha. Okay. Let's get back here. Okay, we have FADH2. Here it is. It's created in the conversion from succinate to fumarate. Succinate to fumarate. That is step 7. FADH2. Cool. There must be a way that I can memorize this. FADH2 is created in the conversion from, yes. The intermediate step between glycolysis and the CAC is called citric acid cycle, stands for CAC. CAC stands for citric acid cycle. So again, the intermediate step between glycolysis and CAC is called the pyruvate dehydrogenase complex. I know that. And it converts pyruvate into acetyl-CoA. And it converts pyruvic acid, to acetyl-CoA. So the pyruvate dehydrogenase complex, it converts pyruvate into acetyl-CoA. Nice. We have something going on here. The intermediate step between glycolysis and, yeah, same thing. Okay, now we have 8 concepts in the same thing. Substrates of the Krebs cycle. Citrate is Krebs' special substrate for making oxaloacetate. Again, citrate is Krebs' special substrate for making oxaloacetate. I'm just drinking water. So, the substrates of the Krebs cycle, I'm assuming it's these 8. Oh, yeah, it's these 8 molecules. I think they're all acids, right? Citric acid cycle. Oh, cool. They're all acids. And it's called citric acid for a reason. Now, I know the citric is related to vitamin C, right? Is citric in the citric acid cycle related to vitamin C? Now we have citrate, isocitrate. Oh, there was a mnemonic for this, right? Like selling seashells for making. Citrate is Krebs' special substrate for making oxaloacetate. Citrate is Krebs' special substrate for making oxaloacetate. I like this instead of that whatever crabs selling seashells. Can I, like, hello officer, can I keep selling seashells for making money? Or like, oh, what could be the oh for making whatever. But this is better. Like, we have to know that eventually this is citrate, which is in the Krebs cycle, and it starts the whole thing, right? Where's the citrate? Pyruvic acid. Oh, here, citric acid, right? Citrate. So citrate is Krebs' special substrate. But this is like not step number 3. We'll definitely check that out. I know. Okay, so definitely step 1 is the pyruvate turning into acetyl CoA, and then acetyl CoA turns into citric acid, right? So if you start from citrate, you know that citrate is, so I is for isocitrate. Cool, nice. Is isocitrate. Krebs, alpha ketoglutarate. Cool. I'm not looking, by the way. So citrate is Krebs' special. Special should be succinyl CoA, which is before succinate. And special, what was the substrate? So succinate, substrate 4, fumarate, making is should be malate, nice. Oxaloacetate, and oxaloacetate is itself. Nice. This is neat. I think I would use this instead. Okay, then we have the Le Chatelier's principle. So Le Chatelier's states that if you add more reactants to a chemical reaction at equilibrium, that the reaction will compensate by creating more products. So the more reactants you add to the chemical reaction, the more products you have. And this concept is right shift. So think of Le Chatelier's like a seesaw that your chemical equation is balancing on. At equilibrium, the seesaw is straight. parallel to the ground. It wants to stay like this. If you add more to the reactant side, it weighs the reactant side of the seesaw down. So it brings down the reactant side. To fix this, the reaction simply produces more products until equilibrium is reached again, and the seesaw is straight. Vice versa with products. Le Chatelier just describes that phenomenon. Oh, when it says vice versa with products, it means that the more you increase your products, the less reactants you want to have to make that reaction in equilibrium. You want it balanced. Interesting. Enzymes do not impact equilibrium. That we know. They just speed up the reaction, right? They will try to trip you up on this on your MCAT. So catalysis equals rate, which equals how fast the reaction occurs. Le Chatelier's equals equilibrium, which equals concentration. Catalysis is a kinetic parameter, whereas Le Chatelier describes responses to changes in equilibrium. So whenever you say kinetic, it relates to the speed of reactions. They will try to trip you up on this again. Yeah. So Le Chatelier's is about concentrations, C Chatelier's, and it's about equilibrium, but catalysis is about rate and how fast the reaction occurs. We have an image here. So you increase the so you increase the concentration of substrate, the direction shifts towards products, and the reason for the shift is additional concentration that needs to be used, right? And then if you lower the concentration of substrate, the whole thing directs shifts towards the substrate, right? So you must make more substance to compensate for what was lost. If you now increase pressure of system, it goes towards side with fewer moles of gas. As pressure increases, volume decreases. Oh, I see. So we have a reason for the shifts and the direction of the shift and the different stressors that are added. This is basically about Le Chatelier's principle, right? So the different stressors that you can have is increase or decrease in the concentration of substrate. So we know that if you increase the substrates, you want to have more products, right? So it shifts towards the products. If you have less substrate, it shifts back. So you want to make more substrates. So the reaction shifts towards more substrate. Is my reasoning correct? Additional concentration needs to be used, right? You have more substrate, so you need to use it more. And if you have less substrates, you must make more substance to compensate for what was lost. Exactly. Now, the next one is increasing the pressure of system. So if you increase pressure, I assume they would increase temperature too. We'll see. So the reaction, if you increase pressure, it goes towards side with fewer moles of gas. This is interesting. So wherever you have fewer moles of gas and you increase the pressure of the system, the reaction goes towards that. Why? Because as pressure increases, volume decreases. Shifting towards side with fewer moles allows equilibrium to offset the new insult. Nice. So because you have increased the pressure, the volume of the system goes down. So if that is the goal, the volume going down, you have to put your focus and shift on less moles of gas, right? So whatever side of the equation has less moles of gas, that side you shift the reaction towards to make it in equilibrium, right? You want to balance it up. So you give more attention to that. It should be the vice versa. So if you decrease the pressure of the system, it means that the volume is going up. So you have, if that's the goal, if you want to increase the volume, you have to put more attention on more moles of gas, right? So the reaction goes towards side with more moles of gas. So as you increase your pressure, the volume decreases. Now we have also the temperature. So away from heat towards endothermic reaction. So if the temperature is going up, you move away from heat towards endothermic reaction because extra heat energy needs to be used. So when you are increasing the temperature, you figured out that you will move away from heat. Why? Because the extra heat energy needs to be used. So to balance it up, because you increase the temperature, you need to balance that out, right? You need to use that extra energy. So you would move away from heat. So you would go towards an endothermic reaction. And if you lower the temperature, it means that you would move towards heat in favor of exothermic reaction. So you would you want more heat energy needs to be produced, right? Because the temperature has gone down. And to counteract that loss, you need to produce more energy. So you go towards exothermic reaction. And from this, we understand that exothermic reactions are reactions that produce heat, and endothermic reactions are ones that use heat. Does addition of catalysts or removal of them affect the Le Chatelier's principle, the equilibrium of the reaction? Hell no. No shift in concentration, because catalysis is a kinetic parameter, whereas Le Chatelier's describes responses to changes in equilibrium. Amazing. That's all the same. Oh, we have something from Psych Soc here. Okay, symbolic interactionism. This theory is often first time I'm hearing this. I think these sociology and some of these psychological terms are just like you're like, what the hell is going on? What is symbolic? Like symbols. Yeah, I know what are symbols, right? Like hand gestures or some signs, right? And then we have interactionism coming from interactions. But does this mean that we use symbols to interact with each other, like the peace sign or the middle finger? Let's figure out. This theory is often overcomplicated and just describes how your experiences add meaning to things like symbols and letters. How our experiences add meaning to things like symbols and letters. For example, you're driving in a foreign country and you see a large metal sign that is red and octagon in shape. What do? You would stop even if you couldn't read the writing, because your experience of driving in your homeland has taught you that a red octagon sign near the road, regardless of the writing, means to stop. Okay, so basically you just see a symbol, um, and you just take meaning from that because you had experienced that before. Keywords, interpretation, symbols, prior experience. Because you have prior experience of that symbol, then you make interpretations. We have social exchange theory. I'm assuming here that we all, coming from social, we all exchange statuses, stati, whatever the plural of status is. Actually, side notes. What is the, let's make it use out of this. What is the plural of status? Statuses, what I said in the first place. You describes, so yeah, social, coming from status, exchanging status. Let's see if I'm correct, or is it just like social interactions? We exchange them to communicate with each other and whatnot. Describes how people from relationships with the intent of maximizing benefits and minimizing risks. Kind of relates to status. So you want to maximize benefits from. So it describes how people form relationships. So you form relationships with the intention of maximizing benefits and reducing risks. So, for example, you date an individual because what they provide, money, love, physical attraction, outweighs what they cost socially, the cost of being taken, the cost of pure judgment for your choice. So so you date that individual because what they provide, like money, love, physical attraction, outweighs what they cost socially. Like, for example, they might be, your date might be, your significant other might be, um, the cost of being taken, like your partner being taken, the cost of pure judgment for your choice, the 10 pounds of muscle they lost when they started medical school, etc. This is personal to the author of this flashcard, whoever made this. Note, this can be also used in an economic sense. People will invest $500 with the intent of receiving $550 on return. Yeah, so social exchange is more about like um, increasing benefits and reducing risks and costs. And it outweighs that, right? Social constructionism. Constructionism. Like constructing something, building something. You built social status, maybe? Claims that intangible things like knowledge, experience, and even words are not real, but carry meaning because individuals and society have decided to give them meaning. So your knowledge from the MCAT, your experience as whoever you are, whatever professional you are, and even words are not real. And as a society, we have agreed to give these things meaning. So these things carry meaning because individuals in society have decided to give them meaning. For example, a dog is a pet, but a wolf is not a pet. Technically, which animals classify as pets is a social construct. Even though I would call the cops and check myself into the hospital if I saw someone walking around a bear on a leash. So it's a social construct that we classify which animals as pets. Well, the meaning is attached to the experience, right? Because you have seen or yourself have experienced dealing with a bear or a wolf, you know they're not domesticated. You know they're a violent animal and they can attack you. That's why you do not call them a pet. Rational choice theory states that actions are always rational in the eyes of the individual making the decision and are made because they are rational. So, rational choice theory, simple, it's called about ration and logic, and it says that actions are always rational in the eyes of the individual making the decision, making the choice, and they are made because they are rational. So also the decision, the choice is made because it's a rational thing. Functionalism is every aspect of society plays a functional role towards a greater whole. I knew that. And for example, a bank gives you a loan to pay for your education so you can become a doctor and treat patients that everyone, including the bank, cares about. Every aspect and institution play their functional role. So the bank will give you a loan to pay for your education so you can become a doctor and treat patients that everyone, including the bank, cares about. Every aspect and institution played a functional role. Keywords in the question stem: society, institution, structures, anything talking about society at large. Anything talking about society at large relates to functionalism. Cool. The institutions, society, structures. That's why we actually have society. It's all about functionalism, providing opportunity for everyone. And then we also have conflict theory. These are major sociological theories. It's actually good to know these. Um, conflict theory. It sees society as a competition and focuses on the inequality between different people. So, wherever there is inequality between different people, it's about conflict, right? Here, you should look for two groups that are clearly in competition over resources or power. For example, the medical school application costs are a conflict between the schools and students because the schools wish to charge as much as they can and still receive the best applicants while the pre-med students wish to pay as little as possible. Especially considering we don't have jobs. Geez, why does it cost so much to apply to medical school? Keywords in the question stem are power, struggle, and conflict. So it's kind of unequal, right? So you have two groups that are clearly in competition over resources, and are the medical schools and students in competition over resources? Um, if it's money, you can say that, yeah. So both students and the schools want money, so the schools will take as much as money they can, and students will give as less as money they can, right? Cool. So we had the symbolic interactionism, we had the functionalism, we had the conflict theory, we had the rational choice theory, we have social constructionism theory. What was that? Social constructs is like we have social constructs like things that we give meaning to, right? Like experience, knowledge. We see doctors as being cool guys who know a lot of shit about our health. And social exchange theory is basically the cost and benefit, right? Yeah. Nice. Let's delve into memory. We have Visual Spatial Sketchpad, which organizes working memory information of a visual or spatial nature. Think navigation. I have never seen this in my life. Visual Spatial Sketchpad? What the hell? It organizes working memory information of a visual or a spatial nature. Interesting. It's used for like think navigation. When you navigate, you just receive you have a working memory from a visual or spatial nature, and what organizes it is the visual spatial sketchpad. We have short-term memory, a small amount of information that is stored in conscious recollection for a small amount of time. Short-term memory is a small amount of information that is stored in conscious recollection for a small amount of time. So we have is sensory stimuli. We have sensory memory, which is iconic visual, less than 1 second. We have echoic, auditory, 2 to 3 seconds. And then you rehearse it like your short-term or working memory, and that is 7 plus or minus 2 items, the 9-digit rule, and it takes less than 1 minute, right? And you encode that short-term memory into long-term memory, theoretically infinite. It's declarative, explicit, conscious, episodic, personal history, events, and experiences. Semantic, general knowledge about the world. So you have 2 types: explicit, conscious, or declarative, or non-declarative, unconscious, or implicit. The implicit part is divided into 3 categories: procedural, performance of cognitive and motor tasks; associative memory, emotional memory, classical and operant conditioning. You associate things, you get emotionally attached to them. It's in the same realm as classical and operant conditioning. And there is a non-associative memory, which is sensitization and habituation. You do not associate anything, you get sensitized or habituated. The first one was procedural, so the performance of cognitive and motor tasks. Now back to the explicit or the conscious. You had declarative, which is explicit and conscious, which is episodic. Like 2 types, episodic or semantic. Episodic is personal history, events, and experiences. Whatever you experienced, event you had, your history is episodic. It's like episodes. And semantic is general knowledge about the world. Semantic is like giving meaning to the general knowledge you have of the world, giving meaning to the world. So short-term memory is in the conscious recollection for a small amount of time. It's less than 1 minute, right? So all these informations, I am absorbing them in less than 1 minute because I'm rehearsing it. Now it keeps getting longer and longer and stays for longer and longer. We need to rehearse it and come back to it, right? We have sensor memory, which is a transient memory traces of our surroundings. This transient memory is of our surroundings. It's just sensory memory. Transient means it's temporary, right? Semantic memory, facts you can recall. Type of declarative memory. Semantic is the facts that you can recall. You recall some facts. It's a type of declarative memory. Yeah, we remember that declarative was explicit, conscious, and semantics is one of the two subcategories, like types of it. It's the facts that you can recall. We need examples of semantic memory. Procedural memory. Memory of how to perform specific tasks like riding a bike or tying your shoes. You want to ride a bike or tie your shoes? Yeah. Therefore, procedural memory is memory of how to perform specific tasks like riding a bike or tying your shoes. Procedural is a procedure. Is it unconscious or is it conscious? Should be unconscious, right? Yeah. Like driving, right? Riding a bike, driving, tying your shoes. Memories can become procedural after practice, like tying sutures will become for the future surgeon reading this. Tying sutures. It's like procedural. Priming refers to one stimulus making recollection of a second stimulus faster or easier. So if one stimulus makes recollection of a second stimulus faster or easier, it is called priming. We need this for the MCAT because the more you prime, the faster that knowledge comes to your head. And it's right there when you need it. Phonological loop. It organizes working memory information of an auditory or written nature. So when you are organizing auditory or written working memory information, is called a phonological loop. Give me a few examples of phonological loop. Non-declarative memory. When you're declaring something, it means that you are saying it, so it should be conscious. When you are not declaring something, it means that it's unconscious, right? So non-declarative memory, type of long-term memory that is implicit or unconscious. Long-term memory, information that has been encoded and can theoretically last a lifetime. So long-term memory is encoded and can theoretically last a lifetime. When you encode it, it's done, baby. This is what I am trying to do here. I'm trying to just encode all this information, and it's theoretically for a lifetime. You have it. You have episodic memory, an event or time period you can recall. So, like an episode of TV, You can recall that episode. It's based on your experiences. And this episodic memory is conscious, right? It should be conscious because you are remembering it. Episodic, yes, it's declarative. Declarative memory, type of explicit or conscious long-term memory. Central executive, it sorts incoming information to either the visual spatial sketchpad or the phonological loop. Nice. So the phonological loop, we understand is for auditory information or written information, and the visual spatial sketchpad is for the vision, like the visual information that we receive. So the central executive is able to sort any incoming information to either the visual spatial sketchpad or the phonological loop. And it is part of working memory, which is functionally the same as short-term memory. So working memory is functionally the same as short-term memory. Oh, central executive is part of the working memory, which is functionally the same as short-term memory. How does central executive function in the working memory? Is it related to the short-term memory too? Short-term memory lasts less than 1 minute. Sure. That's working term memory too, right? Like working short term is the same thing. Sensory memory lasts less than 1 second. Sure. It is very important to know this, apparently. It's sensory. It's less than 1 second. Iconic memory, visual sensory memory. So iconic, your eyes. Conic is visual. Echoic is auditory. You hear an echo. Sure. Classically thought the bounds of short-term memory are 7 plus or minus 2 items. That's the bounds of short-term memory. So 7 plus or minus 2 items. Okay, we have YouTube videos on that too. Cool. Mendelian genetics, my favorite. Not actually. Recessive allele. An allele whose phenotype can be masked by the presence of a dominant allele and requires the presence of 2 alleles to be phenotypically expressed. Note, the recessive allele is still present in the genotype. Yes, I know that. It requires the presence of 2 alleles to be phenotypically expressed. Right, when you have 2 small a's together, AA, in small caps. Haploid, a nucleus that contains 1 of each chromosome for each set of chromosome. There are 23 different types of chromosomes per nucleus. So a haploid is a nucleus that contains 1 of each chromosome for each set of chromosome. Us humans, we are diploids. pH, like phenotype. Oh, we have phenotype and genotype, right? Phenotype describes what is physically expressed or seen. For example, tied tongue. The hell? Tight tongue. Oh, okay. Like you say condition or something. Incomplete dominance. Fun fact, actually, I have a condition with my tongue too. I'll tell you about that later. Incomplete dominance. Neither allele is fully dominant, and the expressed phenotype is an intermediate phenotype. So there should be a complete dominance and incomplete dominance. So incomplete dominance is neither allele is fully dominant, and the expressed phenotype is an intermediate phenotype. A red rose bred with a white rose yields a pink rose. Yeah. Homozygous is when an individual has two of the same alleles as their genotype. Homozygous is when an individual has two of the same alleles as their genotype. So this could be the presence of two dominant alleles or two recessive alleles. That's when you call them homozygous. And heterozygous should be one big A next to a small a. Heterozygous when an individual has two different alleles as their genotype. So two of the same alleles or two different alleles. Alleles, each allele is the big or small a. Two different alleles, big A and small a. Heterochromatin or euchromatin is a more highly condensed and thus less often transcribed type of chromatin. So heterochromatin is a more highly condensed and thus less often transcribed type of chromatin. So the heterochromatin is less transcribed and more highly condensed. Usually U refers to normal, I believe. So I have heard that you call someone when they have a thyroid condition a euthyroid. It means that the thyroid is normal, right? What is the topic? Mendelian genetics. Does the BU in euchromatin means that it is in a normal and general state? So we have heterochromatin, which is a more highly condensed and thus less often transcribed type of chromatin. We have genotype, which describes the genetic makeup of the specific gene in discussion, right? We have dominant allele, which is the big A, an allele whose phenotype will be present if the allele is present. Again, genetic genotype describes the genetic makeup of the specific gene in discussion. So you have a gene, you have a specific gene, and the genetic makeup of that is the genotype. You have codominance. So we had incomplete dominance, which was the pink rose as a result of the red rose and the white rose breeding. Now we have the codominance, which occurs when two alleles are both expressed in a phenotype. Wait a second, wasn't that incomplete dominance? Imagine if a horse had a white allele and a black allele and it came out as a zebra. While that's not the way a zebra's inheritance pattern works, the analogy certainly illustrates how codominance works. Okay. Chromosome highly condensed DNA, chromatin, unraveled and less condensed DNA. So chromosome is highly condensed, and it cannot be transcribed. It needs to open up, right? And chromatin is unraveled in less condensed DNA so that you can transcribe it. And yes, we have chromatin unraveled in less chromosome is highly condensed. We know that also heterochromatin was more condensed, right? Euchromatin is less condensed. Will you draw out every Punnett square even though I know you're smart and would never make a mistake ever? Yes, I will not let the eye of the team down because I know John will. Oh, John was the name of the guy. Will find me if I miss a Punnett square question. Example of dihybrid cross. Just treat a dihybrid cross as two monohybrid crosses and use your knowledge of statistics to answer the question. So, oh, it's break time. I'll be back from the Punnett square for now. Let's have a 10-minute break and I'll be back.